Thank you, everyone. Welcome to this new webinar. In this webinar, we will talk about a new topic for our webinars, which will be beam column steel connection, detailed modeling of beam column steel connections. So just a very brief introduction. So OpenSees and STKO are not widely used for this kind of application, but STKO and OpenSees are general software, so you can also do these kind of things. It's not automated. Probably we will create some automations in the future, but in this webinar I will show you the basic building blocks that you can use to do a detailed analysis of a steel beam column joint. In this first webinar, I will try to keep it simple. So we will do a very simple moment connection, and it will be a welded connection. There is also the possibility to do a bolted connection, but I will keep it for a future webinar. As usual, by today, you will be able to access on our website the recording that is also now live on YouTube. A small presentation, because I'm not going to do all the CAD modeling, otherwise we will waste time. So I have a presentation on how you can build this model from the CAD point of view, and then I will show you what happens if you include or do not include some features inside your model. Okay, so you will be able to find by tomorrow this presentation and an STKO preprocessor file, which will be this one, steel connection, which is the one that I will show you now. Okay, so this is the model that we are going to do. When you will open your file tomorrow, you will find something like this. So it will be already there in terms of modeling. All the components are there. But you will see that you will start with a simple linear elastic material. I will show it to you now. I will show some feature, and then I will show you how to move to nonlinear material for steel, how to add in contact elements, and how to set up the analysis. Okay. So since the geometry is already here, and I don't want to go through all the details of how to model this kind of things, I prepared a presentation. So modeling this is quite easy. In STKO is not parameterized, as you know, there are some commercial softwares which are dedicated for beam column steel connection that where you can build your joints using a parametric approach. In STKO, you have to model it in any other CAD environment, or you can import your CAD model. This is not really relevant. Now, in my example, I built it directly in STKO. This is what the material and section parameters. So a simple steel material, Young modulus of 210 gigapascal, tensile strength and ultimate strength of 235, 360 megapascal. Then I have this beam section, this column section. Here you have the dimensions and the stiffness along the column, which this one is the thickness. Okay, so how do you model this one in the STKO CAD environment to obtain this final three-dimensional model? So it's very easy. Actually, if you have followed all the previous webinars in STKO, you know what are the main tools for modeling this kind of things. But typically, you start by building wires and faces of the basic components. Okay, so in this case, the only three components that I have is the section of the beam, the section of the column, and in the plan view, the plan of the stiffener. Okay, and you just need two comments to do this: lines and planar surface. This is pretty easy. Once you have these basic components, you can just use few other commands: move, copy, rotate, just to move them around, and extrude. So from a face, you can extrude a solid, okay? So once you do that, you will be able to find these first three geometries. So let me show you what they are. So the first one is the column, which is nothing but the extrusion of the cross section here. Same for the beam. These are two separated geometry, as you can see here. They are not connected to each other or not directly connected to each other. Then you have the stiffeners. The stiffeners actually is a compound, if I isolate it, and I show only this one. This kind of geometry is a compound. If you know STKO, a compound is just a group of several geometries. So instead of having 4 stiffeners here, just to keep the tree view more compact, you can join them into a compound. So you have them in just one single group. And same thing for the welds. So if I select this one and I show only the welds, you will see several solid elements. If you want to go in sub-selection, you can go here and select the sub-solids. And to keep them together, since they are separated, you can create a compound also here. So it's very easy to organize the geometry using this approach. There is only one extra geometry that is not really relevant here, but it's a beam extension. So the idea now is to apply a fix here at the bottom, and I need some way to apply a loading on this section here of the beam. So one way would be to apply distributed loading on the cross-section of the beam, which is feasible. As you know, in STKO, you can apply distributed loads following a function of space. But it's much easier, for example, if you attach a beam and through a particular connection that I will show you later on, you can connect the beam to the solid. And it's much easier to apply loads like concentrated forces or bending moments that maybe are the loads that are coming from your global frame model. And it's very easy to apply it here. So that's why I created this extra geometry, which is called beam extension. So it's nothing but a beam with a cross-section, which has the same properties of this one. And everything else is solid, okay? So you can do a detailed analysis of this joint and try to understand how the joint works. Okay, so this one is all about the geometry that we need. As you can see here, these geometries are separated, so we need some way to put them together into an assembly. Because if you have separated geometries, they will not interact with each other unless you physically merge them, like with Boolean operation, or you use interaction to connect them with one another. Okay. So the next step. Oh, by the way, I forgot one step which might be important: how to model welds. So up to here, you just use lines and planar surfaces, then extrusion to create these things. And to create the welds, once again, you just use line and faces to create the cross-section. But then you have the sweep command, which is very convenient, where you can select a face and then a sweep direction by selecting the edges. And you will simply sweep a face along that direction. This is very easy to create a weld geometry. Now, regarding the weld geometry, you can do it like this. But if you create a geometry like this, so a triangle extruded in this direction, you will have a kind of prism with a triangular base. And it is not suitable for a structured hexahedral mesh. So in the next slide, you will see a simple tip on how to set up your geometry in such a way that it's optimal for an hexa meshing, okay? So just make sure that every face, just before extruding them, is made of 4 side edges, okay? So in this way, the face can be meshed with 4 node quadrilateral elements, and then when they are extruded, there will be hexahedral elements, okay? So once you're done with the geometry, you just need some way to put them inside an assembly, so to make them work together. And here we have 3 interactions, as you can see here. The first one is called embed weld, because we need a way to attach the weld geometry either to the beam or to the column, okay? Why? Well, there are actually 2 options to do this. One way would be to take the column, the beam, and the welds and do a Boolean operation, okay, like the merge or the union. The point is that in that way, the mesh should be compatible. So if you want to refine, for example, the welds, you will have to refine also the confining geometries. But this is not necessary, okay? So here I decided to keep them separated and use a particular multi-point constraint to attach them in such a way that I can have uncompatible geometries between the column and beam and the weld itself. So I can use different refinement for the meshes. If you have seen previous webinar, you already know what I'm talking about, which is the embed condition. So how do you set up this condition? Here on the PowerPoint, you will see how to do it. It's a simple connection made of master and slaves. The master is going to be the solid on which the slave faces are attached to. Okay, so if you want to inspect this interaction, you can see it here. So let's go, for example, in geometry, or also here in mesh is the same. If I select this one and you do edit, you can see how I set it up. First of all, you can see that the interaction type is node to element. Okay, so if you remember, a node to node connection, a node to node link is used to create two node links in OpenSees, okay, like zero lengths or rigid links or all this kind of kinematic connection which are node to node. But an embed condition is actually different, is a distributed constraint. So where you have one slave node, which is connected to multiple master nodes. That's why you need the node to element. And the master selection will be the solids, okay? So in my case, the face of the welds are connected to both the column and the beam. So the master should be the solids either in the beam or on the column here. The slave instead, if I select this one, edit slave, now here you cannot see them clearly, but if I isolate them, you will see that they are just the faces of the welds which are in contact with the solid, okay? So for simplicity, I also created selection set. So weld face slave, if you select this one and you isolate it, you can see that they are the faces of the welds which will be in contact with the solid. And the same thing, beam and column solid master. So if you select this one, you will have an easy access to the two components that I used for creating this interaction, okay? Okay, and this one is pretty easy. This one will create this interaction, and if you see here, it will try to connect each node of the weld to the nearest element, okay? And then I will show you what is the condition to assign on top of this one. Okay, so with this first interaction, we connect the weld with the solid and beam. And now we need another interaction. The second one that you find on that you will find on the presentation is the contact. The contact between the contact between beam and column, and between stiffeners and column. Why? Let's go back here. The contact is actually here, the third one. The reason is that now in this case, I'm going to create a welded connection. So actually, the stresses from the beam to the column and from the stiffeners to the column are transferred between one another through the welds. Okay, so for sure, when they are in tension, the forces are transmitted through the welds. But when they go in compression, there is also the contact that transmits forces. So that's why we need contact between these components. As you may imagine, contact is not going to be very relevant in the case of a welded connection, because if the welds are properly designed, they will be able anyway to carry any kind of to transfer any kind of load. So you will not see a huge difference if you include or not the contact. And I will show you this while we run the analysis. But I also included it in this webinar because it may be useful, for example, when you want to create not a rigid connection like this one, but a connection which is more like a hinge. In that case, the contact is necessary. So in either case, I will show you later on what is the effect of including or not the contact. Now, regarding the interaction, is very similar to the embed. Okay, so we want a contact between two faces that may have a non-compatible mesh. So I already gave a webinar on contact, and you know that for contact, I can either use a node-to-node link or a node-to-element link. But if I want to use a node-to-node link, I need to make sure that the two meshes are compatible in such a way that each node of one component, for example, the beam, corresponds to a node on the other component, for example, the column here. But in this case, I cannot guarantee that because for the way I did my geometry, the two meshes are not compatible. For example, if I isolate the column and the beam, you will see that the meshes are not compatible. So I cannot do a node-to-node link, but I can do something else. I can do the node-to-element, okay? So when I do the node-to-element, STKO will try to create a contact between the slave node and the projection of the slave node onto the master element, okay? So behind the scenes, it will do some magic to create another node on that face. And also here, if you want to see what is the master and what is the slave, if I select Edit Master Selection, you will see that I selected all the faces, okay, of the beam column. And with this one is the same selection that you can find here, Contact Master, okay, in this selection set. And for the slave, if I do Edit Slave Selection, now here you cannot visualize it because it's hidden, but it's the same faces that you will find here, Contact Slave. And if I show them only, you will see that they are the faces of the beam, which are in contact with the solid, and the faces of the stiffeners, which are in contact with the column, okay? So if I show everything now, you will see that they are exactly the faces that connects the stiffener with the column and the beam with the column, okay? So this one is a simple interaction to create that will be used for a contact between two faces which have an incompatible mesh. Okay, so now we have everything to connect the welds to the beam and columns and stiffeners, and the contact to connect those faces which are not connected by the welds. Okay, so now the assembly is done. There is only one extra interaction that we have here, which is link beam extension. As I said before, this is not necessary for constructing the beam column joint. It's just a utility that I use to apply concentrated load on a solid domain. So I create a little extension made of beam elements, and you can easily apply connections here, loads here, and they will be transferred to the entire face of the solid. By the way, this is also a nice way that you have in OpenSees to connect models of different details. Okay, so you can create a detailed model of a joint here. You can connect it to an entire frame model, for example. Now, in this case, I'm analyzing only the joint. But if you want to understand what is the behavior of this joint under a particular displacement pattern that is given by a frame model, you can put this joint inside the frame model and use this kind of connection to join the solid model with the frame model. Okay, anyway, what kind of interaction is this one? You can simply go here, edit, and here you will see that it is a node-to-node interaction. Node-to-node because now this one is not a distributed connection like the embed one or the contact one, but is a node-to-node connection, which is in OpenSees is a rigid link. Okay, so if I edit the master selection, you will see that the master is the node here of the beam. And if I edit the slave selection, you will see that it is the entire face of the beam, which is made of solid on the solid domain part. So this basically creates a rigid interaction between this node here and this face here. Okay, so now up to here, your model is done. So this is the main steps that I took for creating the model. So extruding the sections and assembling them together, okay? So once you're done with the assembly, you can go on with your modeling. So for now, I will close this part here, and then we can start by assigning the components in OpenSees, okay? So the first thing that I've done, and by the way, here, what I want to do with this analysis is to understand what is the moment rotation behavior of this joint, okay? I just want to do a monotonic loading, so the only definition that I need is a linear time series. For those of you who are not familiar with OpenSees, in OpenSees you can define how a load evolves in time using a time series. So in the abscissa you have the time of pseudo time in static analysis, and here on the y-axis you have the load multiplier. This one is the typical load multiplier for a monotonic loading. Then we need some physical properties. Now in your model you will see that I prepared 3 different material models. So the first one is an elastic isotropic, so just the Young modulus and the Poisson ratio. We don't need the mass density because we are not going to do any dynamic analysis on that. So why a still model? Because every time you do a model, I always start with a linear elastic analysis, and then if everything is fine, I move to nonlinear, okay? So when you will download this model, you will see that all components have the same material model, which is an elastic steel, basically, okay? Then you will find other 2 material for steel. Now, as you know, steel requires a particular or the most standard constitutive model for plasticity, which is the J2 plasticity or the von Mises plasticity. This one, the second one, which is called steel nonlinear, is exactly the same as the steel here. The only difference is that in the elasticity part, instead of asking for Young modulus and Poisson ratio, it asks for the bulk modulus and the shear modulus, but there are simple equations to obtain them. And of course, you need to assign some nonlinear parameters, okay? In these versions of OpenSees, the J2 plasticity allows for either for either nonlinear isotropic hardening or linear isotropic hardening. Now, in this case, I just wanted to create a nonlinear kinematic hardening that starts the yielding at sigma 0, which is this parameter, and it has an ultimate stress, which is sig inf. It's called sig inf because it tends to that value, okay, but it never goes beyond that value. So if I push it a lot, you will see that it stabilizes around that value, okay? And delta is just exponential hardening parameter. I mean, it's very easy to understand. You can simply, if you put a very small value, it will grow very, very slow. If you put 20, is the one that I calibrated. If you put more, it will grow faster. It's just the rate at which the yield stress approaches the ultimate stress. Okay, so you can use the material tester anyway to calibrate this kind of parameters. Okay, so this one will be the exact nonlinear counterpart of this one. So once we are done testing with the linear model, I will move to the nonlinear one. Then you will find another material, which is the soft one, but I will come back on this later on to explain you why I need it. Okay, so for the moment, don't care about this one. Then you have a 4th physical property, which is an elastic beam extension. It's just an elastic section, okay? If you already did elastic beam sections in OpenSees, you will see that you have here a section to choose the section properties and the material properties for the uniaxial behavior. Why do I need this one? Simply because I have a beam here, okay? So for only this component, I need this physical property, okay? And same thing for element properties. Here you will find 3 kinds of elements. The hexahedron element, which in this case does not have any parameter, which is the brick element that we are going to use for the solid domain, okay? So both the beam, the column, and the welds, and also the stiffness, of course. All of them are made of hexahedral elements, so I need an 8-node brick element in OpenSees. Now in OpenSees you have different brick elements. So if you want to understand what kind of elements you have, you can go here in element property, model, brick elements, and you will find quite a few of them. So the default one is the standard brick. But since we are dealing with J2 plasticity or von Mises plasticity, this is a kind of model that even if the elastic part is compressible because it has a Poisson ratio which is less than 0.5, the nonlinear part is plastically incompressible because of the formulation of the von Mises plasticity. So since the plastic part is incompressible, you have to choose an element that does not suffer from volumetric locking. And these kind of elements are either the complete reduced integration brick element, which is the SSP brick, or the B-bar brick. The B-bar brick is a special formulation that is similar to the SSP brick in a way, let's say, but it only reduces the integration of the volumetric part of the deformation. Anyway, here I choose the SSP brick because it's also faster. It only has 1 integration point instead of 8 integration points like other brick elements. Okay, so just pay attention whenever you use steel plasticity, so the J2 plasticity, pay attention to use an element which is capable of solving the volumetric locking problem. Then you have the beam element here. As I said, it's not necessary, but in this example, you need it just because you have this element here. It is a simple elastic beam column element, nothing special, because we are not interested in what is going on here. And then you have a contact element, okay? So I already explained in other webinars what it is. I'm using the zero-length contact ASDEA implex, which is a particular zero-length contact element with an implex formulation in such a way that it doesn't suffer from the typical convergence issues of contact elements. Here, you just have to specify the dimension, if your model is 2-dimensional or 3-dimensional. In this case, we are in 3D. Then this contact element is based on the penalty approach. So you need the 2 penalty parameters in the normal direction and in the tangential direction, okay? I already explained how you can calibrate this parameter, but it's just a stiff value. So 2-3 order of magnitude stiffer than the typical stiffness of your model. Here you have the friction coefficient, which is going to be the tangent of the friction angle. Now, in our case, this is a typical value of steel to steel friction coefficient. Then you can switch on and off the implex integration scheme. In this case, I'm using it, so it will be faster. And the orientation type, I already explained this one in the webinar about this contact element. But in this particular example, we can use the orientation from element because now we are creating a surface-to-surface contact. So we don't need to specify what is the contact direction because STKO is able to get the contact direction from the master element. Okay, so this is super easy. You don't need to do anything special. But as you can see now, the contact is grayed out. It's grayed out because I didn't assign it. So in the first analysis, I will not use contact and I will not use the J2 plasticity. So it will be a simple linear analysis, both in terms of physical properties, but also in terms of element. I'm not using this inequality constraint. So everything is linear in the first analysis that I will run. Okay, so up to here, we are done with the physical property, element properties. We just need to set up the conditions and to run the analysis. Now, for this kind of model, I have a very few conditions, just a fixity at the base. So I want to create a complete fix. Here, I don't need to define rotations because anyway, a solid doesn't have rotation. But since I'm fixing displacement in the entire face, the rigid body rotation is fixed anyway, okay? So complete fix on the entire bottom face. This is the only SP constraint that I need. Then we need a couple of multi-point constraint. So the first one, you can find it under model, constraint, multi-point, and I'm using embedded node element. So I already explained what this element does, but it is a sort of interpolating. In other software, this is called interpolating element or tying element, but it's just a condition that makes sure that a node moves along the face it falls into. Okay, so that's why it's called embedded node element. For some reason that I don't want to tell here, in OpenSees, this kind of element cannot be added as a transformation element, a transformation condition. So I had to implement it as a penalty-based element. So that's why you have to choose a penalty value. Also here, the penalty value should be few order of magnitudes higher than the typical stiffness of your model. And then you have a few other settings, but if you are interested, we have a dedicated webinar on this element. Okay, so here you just need to set up a proper value. And you can assign it to the interaction, which is this one, basically, the embed interaction. Okay, so this one is the second condition. Then you need another condition, another multi-point constraint, which is the beam solid coupling. This one instead is assigned to this interaction here. As the name suggests, which is this one, is a condition that is used to couple a node which has 6 degrees of freedom, in this case the node of the beam, to a set of nodes with only 3 degrees of freedom, which are the nodes from the solid element. Okay, I already talked about this one. Is actually a combination of two conditions in OpenSees. There is a rigid link and an equal DOF constraint to attach other nodes here to the solid nodes. Anyway, physically what it does is that it transfers the rotation of this node to the displacement of these other nodes according to the distance. That's fine. So this is about essential boundary conditions and multi-point constraints, but then we also have some loading. Okay, so all the loads that you want to apply, you can apply it here. Now in this case, I just wanted to evaluate the moment rotation properties of these connections. So the only load that I applied is a node couple. So a couple here about the global x-axis. Okay, so I just want to create a rotation about the global x-axis. And I applied a positive loading. So a positive loading about the x-axis is bending the beam downward. Okay. As I said before, here I'm modeling in Newton millimeters, but I want the output. Since I know that the order of magnitude of the moment will be of the order of kilonewton times meters, I already put a reference value, which is 1 to the power of 6. So 1 kilonewton per meter, okay, in my unit system, which is Newton millimeters. And it's applied here. If you go in condition, you will see all the applied conditions. Okay, so the applied couples and all the other stuff. Okay, so up to here we have the conditions. We just need to set up the analysis. So what are the typical steps? Well, the first one is to create a recorder. So the recorder is under model, recorders, and PCO recorder. You just choose the name and the kind of variables that you want. In this case, displacement, rotation, reaction, forces, and moments. And then for the element results, since I'm using an under-integrated element, I just want to record strain and stresses. Okay. Then you have to apply boundary conditions. And in this case, you just have one fixity at the base, so one single point constraint, and two multi-point constraints. The embed condition to attach welds to beams and solids, and the link to attach the beam extension to the solid beam. Okay, so these are the only two multi-point constraints. So once you're done with that, we can apply the loadings. And in our case, there is only one load. So we create a load pattern, which is under model, pattern, add pattern, load pattern. In a load pattern in OpenSees, you first define what is the time series that determines how the loads in this pattern evolve with time. So in this case, these loads will evolve linearly in time. And in this pattern, we have only, well, the only load that we define, which is the applied moment about of 1 kilonewton per meter about the global x-axis and nothing else. So just before running the analysis, I set up a monitor because I want to record the moment rotation of this assembly. So I gave it a custom name, moment rotation. In the x-axis, I want to plot the rotation about the x-axis on the selection set called control node. The control node is a selection set using only this end node here. I use average as an operation, and I already explained this one in many examples. Since I'm going to do a parallel analysis, it may have, well, not in this case because this node is on an extremity of the model, so it will only belong to one partition. But in some cases, a node can belong to more than one partition. For example, if that node is on the boundary of two different partitions. In that case, you don't want to sum the rotation of the two parts because they will be similar. So they will be equal actually. So you will count them twice. So that's why in general, when I want to record either displacements or rotations, I just keep the average, okay? At most, it will give me the average of two equal values. So that's not a problem. Instead, for the y-axis, I want to record bending moments and I want them to be in kilonewton meters. So that's why it's very convenient to use the pseudo time, because now I'm going to do a displacement controlled analysis. And in a displacement controlled analysis, the pseudo time is equal to the load multiplier. But if you remember, the final load here will be the load multiplier, which in this case is a ramp that goes from 0 to 1 times the reference load, which is already 1 kilonewton per meter. Okay, so the load multiplier will be equal to the total bending moment in kilonewton per meters. So in this case, it's very convenient. Otherwise, you can use different approaches. So we're going to have rotation in radians and bending moments in kilonewton per meters. And finally, we need to set up the analysis. So it's going to be a static analysis. For the constraints, I'm going to use the penalty method. I already explained the reasons for that, but the beam solid coupling in OpenSees cannot be solved with the transformation method. I'm not going to repeat it again. You will see them in the webinar where we present this condition. So penalty method. Then since this model, well, is not very huge, but I want to take advantage of parallel computing. So I'm using the only available parallel number. Then the parallel solver, which is the MUMS, and then a few other typical settings. So a Krylov-Newton, displacement increment test. Here I'm just using 1 to the -3 because I'm already modeling. My model is already set in millimeters, so I don't need to go too low. This one will be an error of 0.001 millimeters, so it's small enough. The kind of integrator that I want. Well, I applied a node couple, but I want to control the analysis in displacement. So I choose a parallel displacement control. In a displacement control analysis, you have to define what is the control node, which in this case will be the selection set containing the vertex that I want to control, which is this one. The control degree of freedom, which is the rotation about the y-axis, so the fourth degree of freedom in OpenSees, which starts from 1, okay? So 1, 2, 3 are the three displacement, and then the fourth one will be the rotation about the global x-axis. And the target displacement, which in this case is actually the target rotation, because it's the target value for this degree of freedom, which will be 0.05 radians. Now, since I'm not in this analysis here, but after this one, I will apply nonlinearities. So if you expect nonlinearities, instead of using a fixed time step, you can use an adaptive time step. So if you have convergence issues, OpenSees will try to reduce the time step if you are struggling with convergence, and it will try to increase the time step if you are going fine with the convergence. And for that, you have some settings here. But you can use the default, so to control the adaptive time stepping. Okay, so that's all. The only thing that you need before running the analysis is to go in mesh. Okay, here I already set up the mesh, but what I did is to simply define mesh controls, to select all the solids and set up structured and hexahedra. Okay. After that, I defined the global mesh size to be equal to 20 millimeters. Okay. You can go smaller, but this kind of mesh is enough. 20 millimeters is enough. But if you want to investigate the effect of mesh size, you can do that. You can decrease it. And once you're done with the mesh, if you want to run parallel analysis, you have to go in partition and choose how many partitions you want. Okay, now here I have 8 processors. I want to keep some space for the GUI, so I choose only 6 processors, which is fine enough. I have about 1,000 nodes per processor. Okay, so once you're done with that, of course, if you set up your analysis and your mesh to be partitioned, you will have to use OpenSees MP, okay? So the parallel versions of OpenSees. So you choose OpenSees MP and you can finally run your analysis. Of course, this one will show as a linear moment rotation, okay? Just wait a few seconds. Of course, now it converges in just one iteration because the problem is linear. Okay, that's it. So let's go and see first. So this one is the typical step that you do. You want to make sure that your model converges properly because it's set up as a linear. So if you see some struggling here in the convergence in a linear analysis, it means that your model is probably ill-conditioned. So by inspecting the output, you can try to understand if there is something wrong. So the typical thing that I do is to always run a linear elastic analysis and make sure that everything is displacing first and then showing the stress as I expect, okay? So as you can see here, the connection is fine. Even if I'm not adding contact, there is no compenetration down here because now the welds are strong enough to transfer both tensile and compressive forces. As you can see, the embed element is working, is attaching meshes of incompatible, is attaching faces with incompatible meshes. So everything seems to work fine, okay? So the typical thing that you do here is to try to understand if the mesh is fine. And to understand that, you can visualize the stresses. And you can do some analysis to understand if decreasing the mesh gives you a better stress distribution. But in this case, it's not important. So this kind of mesh is good enough. First of all, this one is a linear analysis, but I know that I'm using steel. So the typical stress invariance that I want to visualize when I'm analyzing a steel structure is the von Mises, okay? I look at the von Mises, and the von Mises will be the equivalent stress that will be compared with the ultimate stress in the material model, okay? Now, of course, in this case, this one is a linear model, so you will see that a von Mises stress, which is very high, which means every value here, which is higher than the value that I will put here, is something that will plastify in a nonlinear analysis, okay? So what you can do is you can go here. If you're running just a linear analysis, you can put the maximum and you can see all the elements that plastified, okay? Or you can do something different. Instead of using this one, you can put it as a minimum and using exclude, and you will visualize the results only on the elements that are plastified in this case, okay? Excluding the linear one. So anyway, here you're understanding that a lot of your model is under a plastic range, okay? And especially the welds. In the welds, you can see, so for example, if I go here in geometry and I select only the welds, you will see that the major stress concentration are in welds, okay? Especially this one down here. Okay, so let's see now what happens if I turn this one nonlinear, okay? So when you are confident that your model is running fine, and now let me go back here, is running fine, you can start adding nonlinearities. So first, the first nonlinearities that I add are the constitutive models, and then finally the contact, because the contact is the most challenging one. So start with the nonlinear material. So I simply go here, I select all the geometries from the material steel, and I drag and drop the steel nonlinear. So now you will see that the elastic is grayed out and the steel nonlinear becomes active. Okay, so I already explained what it is. We will see a yield stress at 235, and then it will progressively increase up to 350. Okay, so what I expect is that now that I run the analysis with this one, if I go in the output and I plot the von Mises, I will never see a value which is higher than 350, okay? Because now there is a nonlinear material that is already accounting for stress redistribution due to plastification, okay? So typically, if you don't want to run a linear analysis, you just want to do linear checks, you can use a data range here to understand what are the portions of your models that would have gone into nonlinear regime, or you can directly run a nonlinear analysis, okay? So here you just need to drag and drop the material model and rerun the analysis. Now it will do some iterations, while before it did just one iteration per step. So you see here 1, 2, 6, because now it is approaching the nonlinear part. 31 iteration when it did the jump from elastic regime to plastic regime, and now it does 2-3 iterations because now the solution has stabilized. Okay. Okay, so this one is now our moment rotation diagram. Okay. And let's go in post-processing, reload it. Okay, and now you will see that I don't need to exclude anything. If I plot the von Mises, you can see that now, naturally, no element will go beyond 3 and 50, okay? Now, in this case, it is more than 2 and 35, which is the yield stress that I have here, just because I have strain hardening. So the material is able to increase the stress, but not go beyond 350, which is the ultimate stress. And here you can see what are the zones with major plastification. Okay, so it starts here with the beam. Of course, notice that here it makes sense. So I'm applying cylindrical bending, so only an applied couple. So the bending moment should be constant through the beam. Of course, here it is not because of the connection, but when you are far enough from the end zone here, the beam solution applies. Here you have a slight change in the stress distribution simply because now I'm forcing this face to be flat, okay, which is the beam assumption. But here in the middle, you will see the typical response that you expect. And also you have a lot of plastification here due to shear, okay? So let's bring it in this way. And now you can see also the stress distribution on the welds. So of course, these ones are the welds that are suffering the most. If I isolate welds, select, you will see these ones, okay? And I want to understand what happens if I include or not contact. But in this case, I can already see that I will not see many differences because the welds are strong enough not to allow any compenetration between the bottom of the beam and the column, okay? Now, when can contact be important? Not in this example, because this example, as I told you, as a first webinar on steel joint connection, I want to keep it simple, so I used welded connections. But if instead you are trying to analyze and design a bolted connection that maybe has a hinge-like behavior, not a continuous behavior like this one, then you need contact. Now, in this webinar, I don't have time now to show you how to create bolts, but you can do it. Probably I will do it in a future webinar. but I want to fake it, let's say. So if I want to make this connection here, not a rigid connection, but a semi-rigid connection, okay? Which is something that you may have if you have a certain number of bolts. Now I don't have bolts here, so I fake it by selecting the welds and assigning a modified steel material. Okay, so this steel material is actually equal to this one, but it's softer in the elastic regime. It's just 1% of the initial stiffness of the real steel, okay? So this is not realistic. I just need it to show you what is the effect of contact when you have a semi-rigid connection. Okay, so now you have a nonlinear material for beam and column, the original one, and a fake soft material for the welds, okay? So in this way, I just want to simulate a semi-rigid connection, and now you will see that the contact is important, okay? Because now I'm not using it, and if I run this analysis, you will see that I will have now compenetrations, because now welds are not strong enough to carry all the loads, they will deform, and I will see eventually some compenetration in the compressive zone. Okay, so if I go here in post-processor and I reload it, and I go here, okay, now you will see that the column is not bending anymore as before. You can see that there is a detachment here because now the weld is very soft. As I told you, it's fake, it's not real because a weld is not so soft, but I just want to show you what would happen if you have modeled, for example, a bolted connection, which is, let's say, semi-rigid or actually an hinge. So up to here is fine. The problem is down here. Since we didn't include contact, and if you have a non-rigid connection, the compressive part will compenetrate, and this one is not realistic enough, or at least is not realistic once you reach a higher rotation. Okay, so in these cases, contact may be necessary. That's why I included it in this webinar. So if I go here, I can simply select to turn on contact. I can simply select the interaction I created for contact, and I drag and drop the contact element. Okay, put it here, and I just rerun the analysis. So it's very easy. Let's wait for the analysis to run, and then we will see the results. Now, of course, you see some more iterations because there is also a contact. It's struggling a little bit, but then the adaptive time step managed to bypass the convergence issues. Also here, but once again, the adaptive time step managed to go beyond the nonlinearity. Okay, the analysis is done. We can reload the post-processor. And now you can see that there is no compenetration anymore. Okay, so you can see here what it's going to do. Okay, so here you won't see the compenetration now. Okay, because now you have contact. So here you can see separation. This is fine, perfectly fine. The contact element here is not working. But in this area, and probably it's easier if I show you, instead of the von Mises, I show you the displacement. Okay, so you can see the continuity here. Displacement and magnitude. Okay, so here you can see that now there is not a compenetration anymore. Okay, separation, but not compenetration. So contact, just to say, is not so necessary in welded connection if they are properly designed. You can still include it. It will be more accurate, but they will not play a crucial role. But if you are doing semi-rigid connection, then of course it is important because you are allowing separation. For example, here, this one is the contact element that is separating, but it doesn't allow the compenetration, which is fine, which is what you want to see. Okay, so we are perfectly in time. And yeah, so in this first webinar, I wanted to show you the basic components that you have in in STKO and OpenSees for doing this kind of model. Even though STKO and OpenSees are not specialized for steel joint connections, they are still a general purpose finite element software. So you have all the tools for doing that. Probably in our next webinar, I will show you how to do a bolted connection, but it's going to be pretty easy because we can model bolts with fiber-based beam column elements. We just need contact to create an interaction between the bolt and the different plates, okay? But the component is already here, the contact. So I just need to show you how to create a bolt using an equivalent beam column element. But the tools are here. Or if you have suggestions for including tools like joint modeling in STKO, because probably we will create in the future, not now, but in the future, tools for automating this kind of modeling if the user requests it. Because now users are not using too much OpenSees for this kind of models, but as I showed you, OpenSees after all is a general purpose finite element solver, so you can do whatever you want. Okay, so if there are no other questions, Guido, yes. For the webinar, entire frame with bolts. Okay. Okay, so the next webinar with that, I will show you how to do the bolted connections. So it will be pretty similar to this one. We are just going to, okay, so let's combine three things at this point. I will show you how to use shell elements instead of solids, and how to use bolts made with beam elements and fiber sections. So you will be able to see a complete and coupled nonlinearity in the bolt, because when it plastifies in tension and it goes in shear, for example, you have coupling between the nonlinear Dowell effect there. And with the nice thing with the bolts made with fiber elements is that you can also apply pre-compression if you need it, and it's very easy in a fiber-based section. And I will show you the same example I had here. So how you can put one detailed model inside an entire coarser frame model in such a way that I can show you how to do parallel substructuring. Okay, in the meantime, by tomorrow, you will have both the video recordings, the link on our website. By the way, the link on our website will be, let me go here, because some user also struggle to find them. We can have them in two different locations. So you also have OpenSees support training. You either have them here, advanced e-learning courses, or STKO webinars, okay? So last webinar, for example, was down here. Okay, so I think tomorrow we are going to have it either here. I have to ask Aiden, either here or on the advanced webinars in one of the two parts. By the way,
it'll be here.
It will be there. Okay, STKO webinars.
Yeah.
And you will have a link to the YouTube video and a link to the presentation for the CAD modeling and a link to this model here. Okay, so you can play with it. And yeah, we will let you know when we are going to do the next webinar. Okay, so if there are no other questions, thank you everyone, and thank you for joining this new webinar, and hope to see you soon in the next webinar.